Hello everyone. I welcome to my channel Engineering Technology and Meditation Rituals. Today's topic is on Clapeyron's theorem. A Clapeyron theorem is also known as three-moment theorem. This method in most of the universities is either in structural analysis 1 or in structural analysis 2. This method is useful to analyze continuous beams when number of equations and number of unknowns, if you will compare these two parameters, and if unknowns are greater than the equations of equilibrium available, then we have to go for such types of methods. One of the method is three-moment theorem or Clapeyron's theorem, which I am explaining here. So let us take a simple example of continuous beam. So this is continuous beam ABC with two spans. So this is span 1 and this is span 2. Length of first span is 4 meters, the second span is 6 meters, and this continuous beam is supported by three supports at A, B and C. As you can see here, reactions or the reactive forces offered by these supports are indicated here as RA, RB and RC. The basic governing equation in three-moment theorem is written here. You can see carefully MA into L1. MA stands for moment at A. L1 stands for the span, the length of the span 1, that is 4 meters. MB, moment at B. L1 plus L2, this is 4 meters. The length of the second span is 6 meters. MC, moment at support C, into L2, this is the length of the span 2, which is 6 meter as shown in this figure. 6A1x1 upon L1 plus 6A2x2, or you can nomenclate as x1 bar, x2 bar, divided by L1, L2. So this is the governing equation in three-moment theorem. Now, the first step to analyze by this method is to first of all plot the simply supported bending moment diagrams. So consider this first span AB. In this first span AB, this 6 kilonewton per meter is a uniformly distributed load which is acting on this span AB, and the length of the span AB is 4 meters. So as you have studied earlier in mechanics of solid or engineering mechanics, simply supported bending moment diagram, because of UDL, if you assume this 6 kilonewton per meter as load W, then it will be WL square by 8. So W, which is 6 multiplied by L square, that is 4 square, divided by 8. So 6 into 4 square by 8, it comes 12 kilonewton meter. The same is with span 2, which is here BC. Span 2 BC, the uniformly distributed load is 10 kilonewtons per meter. So the bending moment diagram, simply supported bending moment diagram, will be WL square by 8, maximum at mid. So W is 10 kilonewtons per meter multiplied by 6 square by 8. So 10 into 6 square, that is 36, divided by 8. It comes 45 kilonewton meter. So first of all, you calculate the simply supported bending moment diagram or calculate the maximum bending moment value for the spans given in this figure. Next step, as you all know very well, that we have to calculate A1. A1 stands for area under the bending moment diagram for span 1. That is, this is the bending moment diagram which is parabolic in nature. So this area A1 stands for area under this bending moment diagram. I am trying to show it by the shaded area. A2 is the area under bending moment diagram which is plotted for the span 2. So this area which I am showing here by the shaded red lines, this will be A2. So now you can easily calculate this. Don't get confused with this portion 31.8 and all. I shall explain it later on. So these two bending moment diagrams and area under these bending moment diagrams you can calculate easily to get the value of A1 and A2. So A1 is equal to area under this bending moment diagram. Area of parabola is 2/3. Base is this 4 meters into height, it is 12 meters. So 2/3 base 4 multiplied by height 12, you will get the value of A1. You can see here area of bending moment diagram, it is calculated 2/3 AB into altitude. So it is 2/3 AB, that is base, multiplied by altitude, which is here 12. So this value A1 is, if you can see, this value is coming 32. Now you have to calculate x1 bar or x1. So what is x1? x1 is the distance of the centroid from A. So this length is, either you can abbreviate it as x1 or x1 bar. So this x1 bar will be at mid. It is quite obvious. If the total span is 4 meters, then x1 or x1 bar will be equal to 2. So you can see here the x1 value is L1 by 2, that is equal to 2 meters. Now we have to calculate the value of A2. So again, A2 is area under the bending moment diagram of span 2. So this portion, this area will be A2. So again, area of parabola is 2/3. Base is BC, which is 6 meter, multiplied by altitude or height, which is 45. So see here, 2/3 base into height, A2 is equal to 2/3 base is 6 meters into height. Height is 45. So it is coming, A2 is coming 180. Now how to calculate x2. So x2 is the distance of centroid of this parabola, which is bending moment diagram for the span 2, and this distance is from support C. So again it is 6 by 2 because the centroid will lie at the midpoint. 6 by 2 is 3. So the value of x2 or x2 bar will be equal to 6 by 2, that is equal to 3. So this is written here. Now if you will look at this equation, L1 is known to you, which is 4 meters. L2 is also known to you, length of the span 2, which is 6 meters, right? L1 is known, L2 is known. You have just now calculated the area A1. A1 is the area of this bending moment diagram for the span 1, which you have calculated as 2/3 base into height. Then A2 is the area under this bending moment diagram, which is again 2/3 base into height you have just now calculated. X1 is the distance of centroid from A. X2 is the distance of centroid of this bending moment diagram from C. So this way you have calculated the values of almost all the unknowns except 3. The first one is MA, which you don't know the value. Second one is MB, you don't know the value. And the third one is MC. So now you have 3 unknowns, MA, MB and MC. And the equations of equilibrium available with you in this case are 2. Summation Fy equal to 0, summation of the moment, sum of all the moments about any point within the beam is equal to 0, Clapeyron's theorem. You will not consider here the summation Fx equal to 0, that the sum of all the horizontal forces about any point within the beam is 0. You will not consider this because we are not considering axial deformation. Without axial deformation we are trying to analyze this beam. So equations of equilibrium available with you are 2 and the number of unknowns are 3. So this you cannot solve using this single equation. So for this you need to minimize these 3 unknowns to 1 or 2 unknowns. So if you will see this continuous beam, you know very well that the moment at the support is 0. The moment at this support C is always 0, because if you will try to draw the deflected shape of this beam because of loading, you will get something like this, right? Sorry, the deflected shape, if you will try, you will get like this, right? So here the moment will be equal to 0, here the moment will be equal to 0, and at support B you will get the hogging moment, that is, I always consider hogging moment as -1. Here you will get sagging moments, here you will get sagging moments because of loads, because sagging moments are the function of loads and hogging moments are the function of supports. So in this way MA and MC is now equal to 0. So you can easily calculate your 3 unknowns are converged into the single one, that is now MAMC equal to 0. So the only unknown which is existing is MB, and very easily if you will put the values in this equation as I have just now explained you, that MA will be equal to 0, MC will be equal to 0, L1, L2, A1, X1 bar you know very well. So you will get the value of MB. Now this is the value of MB which you have opted. Now how to plot the bending moment, net bending moment diagram? You have calculated the value of MB. Now see here, first of all you have to plot the simply supported bending moment diagrams as you have plotted here, right? WL square by WL square by. So these are the bending moment diagrams because of loads, that is the sagging one. Then you have to plot this hogging moment MB which you have calculated 31.8. So 31.8 actually the hogging bending moment is negative. If I will try to plot positive above the line and negative below the line, I cannot overlap the bending moment diagrams, and overlapping is necessary so that I should know that what is the neutral area. So for here 31.8 is the negative bending moment which I have plotted here above x-axis. This also I have plotted above x-axis so that plus minus will get overlapped and I will be able to judge the neutral area. So now this hogging bending moment also I have plotted with straight line 31.8. Now this positive and negative whichever I am coloring here, this is the neutral area. Neutral area means positive plus negative equal to 0, and this portion that is the maximum ordinate is 31.8 is the hogging bending moment. This portion is the sagging bending moment, but this portion is not 45 kilonewton meter. It will be 45 minus this ordinate. In this way, if in practice you want to design the beam, so you should design for 31.8 as hogging bending moment and 45 minus this portion, this ordinate. You will get this net positive sagging bending moment. So this way you have to superimpose the bending moment diagrams and you have to analyze such indeterminate beams. I hope you all might have enjoyed this lecture. So this is a simple example where we have analyzed the continuous beam using Clapeyron's theorem. Thank you. Thanks for watching this video.